In this video, I'm going to solve this Euler's equation. It is x square y double prime minus 3x y prime plus 9y is equal to 0 with positive x, meaning x is greater than 0. Now, let's go ahead and try to solve it. Our general assumption is that our solution is of this format. Y of x is equal to x to the power r. Then y prime is going to be r x to the power r minus 1, and y double prime is gonna be r times r minus 1 times x to the power r minus 2. Now I'm going to take this y prime and y double prime and plug it into this equation. Once I do that, I get the following. Basically, after doing some algebra, I'll get this expression or equation rather, where this cannot be equal to 0. X to the power r cannot be 0 because it's an exponential. And that kind of leaves me with this to be 0. So which is to say r squared minus 4r plus 9 is equal to 0. Now this is a quadratic equation in r. I can use the quadratic formula and solve for r. If I do that, finally I get the complex conjugates. R is equal to 2 plus or minus square root of 5 times I. So my solutions are going to be of this format. So y is going to be x to the power 2 plus or minus I times square root of 5. Easier. Remember, I is outside the square root. So this is what it's going to be. So now let's go ahead and take just one of the values, okay? Not two of them, just one. X to the power 2 plus I times square root of 5, okay? I could simplify it to x square times x to the power I times square root of 5, okay? Now that I could further simplify to the following: x square times, now this x to the power I times square root of 5, I'm going to rewrite it as e to the power ln of absolute value of x times x raised to the power I times square root of 5. So this is important for you to kind of follow. So remember, ln and exponential functions, they're inverses of each other, so they cancel each other out, okay? So if you have x, you could write it as e to the power ln of absolute value of x. We are assuming x is positive, or x could be written as also ln e to the power x. So that's the property that I have used here in rewriting this thing as this. So what I'm going to do, I'm going to simplify it further. So x squared, so let's put it here inside a square bracket so that you can see it clearly. Now that's going to be the same as e to the power I times square root of 5 times ln of absolute value of x. What did I use here? Remember, ln of x to the power a is a times ln of x. That's the formula I used in simplifying this, because it has ln absolute value of x raised to the power I times square root of 5. So that's what I have used. Now, let me remind you here of another formula that you have seen before. E to the power I theta is equal to cosine of theta plus I sine of theta, okay? E to the power I theta is cosine of theta plus I sine of theta. By using that, I'm going to simplify it. So it's going to be x squared times cosine of theta. So in our case, it's going to be cosine of square root of 5 times ln of absolute value of x plus I times sine of square root of 5 times ln of absolute value of x. And let's put it inside the square bracket. Now I just distribute the x squared. If I do that, I get the following. Now my solution is going to be of this format. Now there is a plus or minus here, so if I wanted to evaluate the minus sign, then it would just be this negative. So just by looking at it, I can see that my solutions, independent solutions, are going to be my y1 of x is going to be x square cosine of square root of 5 times ln of absolute value of x, and my y2 of x is going to be x square times sine of square root of 5 times ln of absolute value of x. Now your general solution is going to be nothing but a linear, arbitrary linear combination of these two, right? So it's going to be y of x is equal to c1, some arbitrary constant, times y1 of x plus c2 times y2 of x. And let's go ahead and write it out. Once I write it out, this is what I get. This c1 y of x equal to c1 x square cosine of square root of 5 times ln of absolute value of x plus c2 times x square times sine of square root of 5 times ln of absolute value of x. So this is your general solution to this Euler's equation. When the roots are complex, this is the general process that you'll always use, okay? When you have a characteristic equation with complex roots or complex conjugate roots, this process should always work, and finally you should come up with some expression like this. I hope that this discussion was helpful. Thank you very much.